Hello. Hello. Am I audible, sir?
Yes, madam, you are audible.
Yes. A very warm good evening. So, I will start today's session. Okay, so I hope that my screen is visible.
Yes, visible.
Yes. So, in today's lecture, we will first try to revise the optimal extraction of non-renewable resources part, and then we will go towards the optimal extraction of renewable resources, and then we will finally learn the tragedy of commons. So, in the last session, in the last week, we have covered natural resources, economics, and dynamic optimization. So we have defined the natural resources, and then what are the conditions uh, for a resources to be considered as natural resources. So it should be socially accepted, technologically available. So there should be feasible technology, and then it should be economically feasible for, or it should be cost effective. So any resources which fulfills all these three conditions can be considered as natural resources when it occurs naturally in the environment. After that, we have defined the renewable resources versus non-renewable resources. So the main, hello, sir, are you trying to say something?
Nothing, madam. So I'm muting.
Okay. So then we have tried to differentiate these two thing by saying that the only difference is that those naturally occurring resources which are having its own generating capacity, then only it is called renewable resources. That too, the regenerating capacity should be within the economically feasible time horizon. Let's say that even the coal or any oil also regenerate itself. However, the time duration which is needed for regeneration is very large. So such kind of resources which do not have regeneration capacity within the feasible time frame, these are defined as non-renewable resources. After that, we have asked the question whether there is a possibility that renewable resources may also get exhausted. So over the lectures, we have decided that always for optimal usage of resources, the rate of extraction should be less than rate of growth. So the main condition when the renewable resources get exhausted is when the rate of extraction is more than rate of growth. So in such condition, then the resources may get exhausted. Also, due to change in the climatic condition, there might be impact on the species of animals due to which they extinct. So these two reasons are uh, those which will impact in the exhaustion of renewable resources. After that, we have asked the question that what is optimal utilization or optimal extraction of resources. So for optimal extraction of resources, the rate should be not too much, not too slow. Not too slow will lead to the uh, lesser growth of economy, and too much of extraction will lead to the environmental degradation and exhaustion of resources. So now how will we define the optimal rate of extraction, right? So the rate of extraction that maximizes the temporal benefit. So over the time, let's say that you have certain stock of coal, then how much rate of extraction each year you have to derive so that your overall benefit is maximized. So in this kind of optimization, you have optimal solution at each of the time block from t is equals to t1 to t is equals to capital T. So this is not a static optimization in which we get one solution x comma y, but you get x1, y1, x2, y2 till x capital T, y capital T, right? So this kind of optimization is known as dynamic optimization, which is time dependent. So optimum rate of extraction is derived by dynamic optimization. So after that, we have also noted that the natural resources are not closed set. However, it is a open set. So new element might add or existing element might get eliminated from this set. So I hope that you catch up this part, but still it is a part of my session. So I will be going through this a little bit faster maybe. So if you have any question, then you can stop me in between and then you can ask. Okay, sir?
Okay, madam. So you,
Yeah.
yeah.
Any point you want to make or any discussion till this point?
Nothing, madam. So you complete. Then I make notes and I'll ask later.
Sure,
Yeah.
sure. Okay, now we have dynamic optimization part. Okay, so now in a normal ordinary good, what we do is we compare the price with marginal cost of extraction, and the price is determined by this MC, that is marginal cost of production of a any good or any service, right? For ordinary good. However, for non-renewable resources, this cannot be applied. Why? Because let's say that you are using certain non-renewable resources right now, but this resource have some opportunity cost. So this is very important part of non-renewable resources that right now you have, because this is the opportunity cost right now you have, because of which you can use it. So this, the cost associated with the present utilization of non-renewable resources can be known as the marginal user cost. So uh, this is uh, associated with the opportunity cost of utilization of resource at present. So because of this utilization, the resources will not be available in future. So that is why the price is equal to marginal cost plus marginal user cost. So in this curve, you have quantity of good in the x-axis and price of good. And let's say that this is the price path for marginal utility ordinary good. Then augmented marginal price, that is equal to marginal cost plus marginal user cost, will determine the cost of non-renewable resources. So now let's say that for time t is equals to 0 to t is equals to t1. So we are taking two period, that is first period and last period, and the price of each of the period are defined as p0 and p1 at time t0 and t1. Okay. So now the resource owner have to decide whether to use the resource at present or keep it for tomorrow. So now for this, we what we have to do is we have to define a benefit, right? So benefit is given by the rent of resources or the function where we subtract the price with marginal cost of extraction. So this term give us the benefit. So what is my benefit? That is the price which I'm getting minus the cost which I'm incurring, right? So at if I use at P0 T0, then my benefit will be P0 minus marginal cost of extraction. And if I use in future by keeping it for tomorrow, then the price will be P1 minus, then the benefit whole will be P1 minus marginal cost of extraction. So now if I discount it to the present, then I will get the present value of each of the benefit. P0 minus MCE, same. And here in this term, since it is for the future, 1 year T is equals to 1. Therefore, I am multiplying the term 1 plus R to discount the value. So these are both the benefit of present, benefit of future. Okay. Now it is very obvious that I will always choose the higher benefit point, right? let's say that if my point A present benefit is more than future benefit, I will use it in present. If future present benefit is less than future benefit, then I'll keep the resource for future, because in future the price may get higher and I will get more benefit. So I will keep it for future. And if these two are equal, then I am indifferent between the utilization of resource today or tomorrow. So these are the three conditions which we have derived, that present benefit is more than future benefit, less than future benefit, and equal to future benefit. So this,
Madam, just one question here.
yes, sir.
You see, the same economics equation for normal goods versus the environmental good. The difference is that the future marginal user cost that is represented by 1 plus R, right? Discounting. That
Yeah.
is the that's the
No,
only
no, no.
difference, right? One.
Here, this is not one plus R is not the term here. The For now we are not giving the marginal user cost term. This like this
Okay.
slide and next slide is totally different. So right now we are not deriving the value of future marginal cost. Right now what we are, in the future slides you will get to know. But yeah, our
Okay. Okay.
time multiplied. Yes. So now let's say that here, let's say that this term which you are asking, right? Okay, I got your point. That is, this term is marginal user cost. That is the opportunity cost. Is this what you're asking?
Uh, yes, madam. Exactly.
Yeah, yeah, yeah.
So that is the one which makes a difference between normal economics goods versus environmental goods. Correct? Yeah.
Yes, 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 yes.
Yeah.
That
Okay.
is correct. So this is some cost component which is associated with the utilization of resource today versus keeping it for tomorrow. And now from this equation, this equilibrium condition equation, we are deriving the value of P1, that is price of good at time 1. Then we will get equal to marginal cost of extraction plus P0 minus MCE times 1 plus R. So you are taking all this term to the left hand side and deriving the price P1. So if you generalize the value, then Pt, where t is the time, will be equal to marginal cost of extraction plus this term. Okay. So this equation is known as general expression of price path for optimal extraction. So now what optimal extraction means. So let's say that you choose to keep the resource for future, however you do not get even the benefit which you will get out of keeping the money you get, like keeping the benefit you get in the bank also, then it's of no use for keeping the resource for future. So therefore we are saying that at least it should be equal to the present benefit. So therefore we are equating the present benefit with the future benefit, and then we are getting the equilibrium condition.
Madam, just one confirmation. I'm trying to make an intuitive sense of the term PT is equal to MCE plus P0 minus MCE into 1 plus R to the power of T. So what it means intuitively, that marginal cost of extraction keeps on increasing with time because you are depleting the resources, correct? Over a period of. So, for example, every year, the marginal cost of extraction keeps on increasing. Am I correct?
In this case, right now MCE is constant. We are equating PT, right? So this
PT.
price will be keep on increasing, because
Increasing.
yeah, because with respect to
Yeah, yeah.
time, there is a interest
Yes.
value also, right?
Okay.
So even if
Okay.
you
Okay. Exactly. Yeah.
yeah,
Yeah.
so
Exactly. Exactly. What I mean is, see,
uh-huh,
generally in a normal economics, the price is dependent purely on the cost of production.
uh-huh,
Here,
uh-huh.
that the price is dependent on marginal cost of extraction over a period of time. It keeps on increasing after year. Cost
Yes,
of
yes,
extraction keeps on
yes,
increasing. Okay. Okay. Got it. Got it.
yes. So okay, now Now let's say that we are out of this equation, right? We have P1 equal to MCE plus, uh, sorry, I'm getting some noises. If possible, can you mute yourself? Uh, Polymony,
Yes, ma'am.
yeah, can you please mute yourself? If you have any question, then you can ask me. Otherwise, please keep it muted so that there is no noise. Okay. Do you have any questions? Okay. Now we are good to move. So now we are getting the value of r. Okay, so in after rearranging all this, we are getting r is equals to p1 minus mce minus p0 minus mce whole divided by P0 minus MC. So it is kind of a growth of marginal resource rent. So this term, right? This term, how it is growing with respect to present towards the future. So what is the growth of resource rent? So this is represented by my R term. And this R term is also known as the rate of interest or rate of discount. So in the like the discount or interest rate determines the determines the growth of marginal resource rate. So that is how we are deriving out of all this uh, derivations. Okay, all this uh, equations. So now uh, uh, from here we can say that in the Hoteling's rules, what we say is that the most socially and economically profitable extraction path of non-renewable resources is along the marginal resources range must be grow at the rate of discount. So it is similar as what we have derived here. So the this marginal resource rent, that is P minus marginal cost of extraction, should be grow at least at the rate of discount. So if this is being followed, then we are at the optimal extraction pathway. Otherwise, we are not at the optimal extraction pathway. So this is the one primary condition that optimal extraction of resources is being followed or not. So any questions or any comment you want to make on this? So from
Nothing, madam.
yeah, so from here we have derived the R value, and then we have stated the Hoteling's rules, which say that the optimal extraction of resources is when rate of interest or rate of discount is equal to the marginal growth of resource rent. So let's say that you have rupees zero at time, sorry, rupees one at time zero. Then at least you will get 1 plus R, where R is the rate of discount, right? So if my resource rent is like my benefit right now is this, then at least my future benefit should be P0 minus MCE times, sorry, P1, this is incorrect, P1 minus MCE times R. So, okay, no, this is P0 only. Uh, this term should at least grow by this value. So that is what we are saying. So now from here we are getting this condition, and now we have said that optimal extraction also depend on two things, that is P1 and R, right? So P1 is expected price of future at time 1 or any time t, or and then R is the rate of discount. So rate of discount is person to person dependent. Let's say that I have a stock of oil in some reservoir. So for me, if usage of present have more value than future, then like let's say that if I need money right now very urgently, then for me I'm more present biased, right? But let's say that if I want to secure money for my future generation or for the future, then I will be future biased. Based on present bias or future bias, the discount rate will be different. So let's say that R is dependent on person to person. Present bias individual have more R than future bias individual. So then present bias individual will try to extract resources in present as much as possible. Okay. So now from this equation, let's say that we have general expression, right? So in this equation, we have PT. So let's say that in this case, this term T, as T tends to infinite, my whole term is tending to infinity. So indirectly, it is saying that after a sufficiently long amount of time, price of non-renewable resources will become infinite. So if you think that will the price of coal in after like let's say that 100 years will it be infinity? So does pt become infinite as t tends to infinite? So the answer is no, and there are two reasons which we have stated. First one is that the current expression which we have derived is only done by considering the supply condition. The demand condition is not considered, and price is always determined by demand. So it will not become infinity. Also, after certain amount of time, when the price becomes very large, we will look for alternative solution. There will be more innovation, and we will get the substitution of this resources, right? So this kind of resource can be known as backstop, where availability of alternative or substitute goods or resources, or it might be technology, which makes the utilization of existing resource more efficient. So this technology, let's say that after 50 here, maybe we can move fully towards the renewable energy such as solar, wind, hydro. So right now we have certain coal stock and our economy is backward. So maybe we can extract more resources right now. So those resources like solar, wind, hydro, such kind of resources can be termed as backstop. So since we have alternative resource, we will efficiently extract the resource right now. Okay. So now the answer to the previous question, that will price in the time t when t is very large, let's say that will the price of coal be infinite after 200 years? And the answer is no, it will not be, because at that time maybe we will have more efficient technology. At that time maybe we will have alternative technology, or at that time maybe we don't have any demand for the coal. So these all reasons concluded that the price will not be infinity. After that, we have now tried to find the marginal cost of extraction of backstop. So marginal cost of extraction of backstop in this curve is determined here. This is my time as x-axis and price as y-axis. Okay. So let's say that for non-renewable resources, the cost of extraction, marginal cost of extraction is this one, and for backstop, marginal cost of extraction is determined by MCB. Okay, and at time capital T, uh, we will uh, uh, we will exhaust all the non-renewable resources and we will move towards the backstop. So uh, one of the benefit of backstop is that once we move towards those technology, there is no user cost. That there is no user cost because it will be available for certain amount of time after the utilization. So let's say that solar energy or hydro power plant or anything. So this plant do not have opportunity cost of using right now. So for those plant, the price is merely given by MCB. However, for non-renewable resources, the price will be marginal cost plus marginal user cost, which is associated with the uh, utilization of resource right now, right? So now from here we have two equations. Equation one is a general equation which we have derived previously. Equation 2 is price of backstop at time t is given by marginal cost of backstop. So at time t we have two equations, price given by this, price given by this, and this two will be equal, right? So when these two are equal, then what we can say is that now we are equating 1 and 2, and we have derived price at time t as a function of marginal cost of backstop. Okay, now this equation After arranging all this, we have derived the equation, and we have uh, summarized two inferences. The first one is the marginal cost of extraction of backstop determines the price path of existing resource. Why? Because this PT is price of uh, non-renewable resources, right? However, when we do this marginal cost of backstop, when we get marginal cost of backstop in this price path, more is the marginal cost of backstop, more will be the price. If we have alternative technology or alternative backstop option at lower marginal cost, then the price will not vary that much. So that is what it is trying to say. And the second inference is marginal cost of backstop sets an upper limit on the price of existing resource at time period t. So these are two conclusions. Uh, Now we will try to look into the static optimization and dynamic optimization. Okay, so static optimization is, let's say that you have a utility function, let's say maximization of utility with a product x and y. Okay, and you have income constant, price multiplied by x and price of y multiplied by y is equals to I. So in this case, if you maximize the function, you will get optimal value of x star and y star. However, in dynamic optimization, we are taking a case of 5-year economy of a country. Okay, so this diagram represents the 5-year economy of, let's say, India. Now, Now, from time 0 to time capital T, we have 5 year. Okay. So at each year, you have to invest certain amount of time, sorry, certain amount of money, so that the state of economy 0, A will improve to the T, Z. Okay. So 0, A is initial state of economy and T, Z is terminal state of economy, where Z is the capital stock. Okay. So uh, now let's say that from A you can go to B, C, D, E, and T. So A to B there is some association of money. B to C there is some association of money. C to D there is some association of money. So that association of money is the investment amount. Okay. So each year you are investing something. So you are moving from A to B. Since you are investing something, B to C and so on. Okay. So now we have different paths, the set of paths which we have shown here. And now let's say that which path will you choose? So I am uh, I am a policymaker. Let's say you are a policymaker, and then you have to choose the pathway of India of 5 year from this economy A to economy T, Z. Okay, so I will choose the minimum investment, right? I will choose, my initial state is fixed, final state is fixed. So I will choose the path which will lead to the minimum investment amount. So now let's say that in the A, M, N, O, P, Q, I will sum all the investment, and in the same way A, B, C, D, E, and then final. So if I sum all the path in all case, then I will compare the minimum investment situation. So it is overall cost of investment, right? So it is a travel cost rather than one time investment. So in this case, myopic vision is not chosen, but overall traveling cost is considered. Okay, so the time we have considered over here is discrete time period, from time is equals to 1 to time is equals to 5. Okay, so similarly, we can generalize for the continuous time period. So 0, A to the 0, Z. So my final state. So these are the pathways C1, C2, C3, and C4. So the minimum travel distance will be in the case of C2, right? So this will be my least cost way to go from 0, A to the final economy. So I will choose C2. Okay. Now, what are the important elements of dynamic optimization? The initial state, terminal state, the paths which we have the decision variable. In this case, we have taken the investment, and then we should have an objective functional. Okay. So now objective function and objective functional's difference is that in objective function, we are mapping one bundle to a utility. Let's say that you have certain x comma y and you have u value, right? But in objective functional, in the case of dynamic optimization, you are mapping paths z, which is the sum of paths. So you have certain integral value of different paths, path v1, path v2, v3, and so on. So path v of y of t, where yt indicates the path and v of yt indicates the integral value of path. So in such case, where you have certain integral value of path and then you are trying to find the optimal path. So this kind of objective function, this kind of objective is known as objective functional, uh, in opposite to the objective function in the case of static optimization. After that, there are another cases where our terminal state t comma z, right? In the previous case, my t comma z is constant. All the path will converge to one final state. However, there might be some cases in which my z are different. So my final economy state is different. Then uh, and my time is fixed, time 0 to t. In this case, what will be my objective? So we will choose the terminal state which gives us maximum z, maximum economy state, that is achieved at minimum cost. So this will be my objective when the time is fixed. Okay. In the case when z is fixed, my final state is fixed, but my time is not fixed. Then what will I choose? I will choose the path which minimize the time. So this my t1 is the minimum time to achieve the economy z. So in this case, I will try to find the minimum time. Okay. Okay. Now, there is another case where t and z are variable also, which we are not discussing right now. Okay. Now we are summarizing this part. So in the economy that begins with initial capital stock, and our aim is to reach a desired capital stock, that is capital T comma Z, and the decision variable is investment made over the period. So the objective is to achieve the terminal capital stock at minimum possible cost. So this is what we have discussed in the dynamic optimization case. Okay. And we have also discussed the key elements of dynamic optimization, that are initial and terminal state, decision variable, objective functional, and optimization process, right? So with this, we are moving to today's session. So if you have any question, then we can maybe ask, you can ask, or you can ask at the end. Sir, any question till now?
Okay, no question, madam. You can
Oh,
proceed.
sure, sure. So I'll proceed forward. After that, we have tried to relate this to the non-renewable part. Okay, so in non-renewable, you have two benefits which you are drawing out of non-renewable resources. First one is flow benefit and scrap value. Scrap value is the value which you are getting at the end of resource utilization. Let's say that the time of resource extraction is from 0 to t, then scrap value, which is defined as f, will be function of x of t, where x of t is my stock. Okay, so this is my time. Time is equals to 0 to time capital T, and at here I am getting the scrap value, and over this time from 0 to capital T I have some flow benefit. Okay, so my
Madam, just one question to trying to understand what is scrap value. For
Hmm.
example, you take a coal, which is a non-renewable resource. Let
Mhm.
us say after 50 years, what is scrap? What do you mean by scrap value of coal?
Okay, sir. Matlab, as far as we know that at the scrap, normally, let's say that you are utilizing certain resources, right? So at the end of the utilization of resources, what is the value of that resource? That will be a scrap value, right? So let's say that you have a certain reservoir of coal you are extracting over the time, and at the end you have certain coal stock. So that value of coal stock at the end, let's say if you are selling this, let's say that you can sell that coal stock, then what will be the value? So that will be the scrap value, and the value which you draw in this 50-year, so that will be your flow benefit. Did I answer?
Mm,
So at
yeah.
like let's say that you have a coal plant, right? So coal plant you are using over the time, so you are generating electricity and you are getting benefits. So that is the flow benefit. But at the end, what is the value of this machines, this all the buildings and all? So that is the scrap value.
No, I understand as far as machinery is concerned, it's
Hmm.
fairly intuitive. But scrap value of non-renewable sources, that is what I'm trying to understand.
That is to some
Uh,
extent like the value of reservoir, as far as I can think of, it is the value of the reservoir which you have. Like it will be totally dependent on the value of stock, right? Stock, that is x of t. So it will be the final value, that more is your stock, more will be the scrap value. So that is
okay.
what I can understand from here. So if you have anything to add, then maybe.
No, no, I am trying to visualize. For example,
Hmm.
we are using a coal-based thermal plant, and we have been extracting coal and generating power, and that is a flow benefit. I understand perfectly. Let us say after 50 years, the
Hmm.
coal got exhausted, and what I thought is the what is left is ash, which is a useless thing. I am
Oh.
assuming that is a scrap. I don't
No,
know.
no, no,
When
no.
you
That no, that is not the case. Let's say that if you are the owner of coal power plant, then your scrap value is the machine or the building which you have, right? So that will be the scrap value. But if you have a coal stock, let's say that you are the owner of a certain mining mountain, then you are
yes.
deriving certain benefits over the time, and at the end, if you want to sell the mountain, let's say you are a businessman, you can sell it to some other person maybe. So that will be dependent on the stock you have, right? So that
Okay.
like that value can be termed as scrap value. So this is my
Okay, no,
understanding.
I got it, but where the words actually that is what is the value of the remaining stock? Okay, that the
Mhm.
coal doesn't become scrap, without using. No, I'm just trying to the vocabulary is where.
Okay.
Yeah,
uh,
vocabulary in terms of machinery, I understand there is a depreciation, there is no value
yeah.
after machines. Sometimes we use it with scrapping cars, after some time there's no value with it. But when
Mhm.
in a non-renewable resource like a coal is there, so let us say
Mhm.
I have a mountain of coal. Okay,
Mhm.
I
Mhm.
have been using it, I've been making money by selling coal, and
Mhm.
I reached that period where there is only 10 tons of coal. Do we
Mhm.
call that as a scrap? I don't.
Yeah, well, the terminology wise, yeah, I agree with you that you cannot say scrap, but matlab maybe sir is trying to compare it with a normal knowledge of economy, right? Normally, let's say that if you discount something, then you get at the end some scrap value. So that is why
Okay,
he's trying to call it
okay,
the scrap value, as far as I understand.
okay, thank you. Go ahead.
And
Go ahead.
now we have our objective, which is maximization of flow plus scrap value. Okay, so that is overall benefit which you have out of non-renewable resources, and the flow value is defined by the integration from time 0 to capital T and then the flow, and scrap value is determined by f of xt. Okay, now we have two variable here, that is x of t and y of t, where y of t is rate of extraction and x of t is stock value at time t. Okay, now our flow function is function of rate of extraction as well as stock value. More is the stock, more will be the flow benefit, and more is the rate of extraction, more will be the flow benefit, but it will be dependent on the stock value also. If you don't have stock value, then you don't have flow benefit, right? So these are all functional. Okay, now we will move a little forward. So we are trying to maximize the flow value and scrap value. Our objective is the change in the rate of change of stock will be function of rate of extraction and stock. Okay. So this x dot t, that is differentiation of x with respect to time t, is a function of how the stock of resources will change over the time period. So okay, so this is also known as dynamic constants. Okay. Now after that, what we are doing is we are trying to derive the okay, I'll remove this so that okay, now we are trying to derive the Lagrangian function. So our objective is v dot integration over time and then the scrub value, right? Now we are multiplying lambda with our constraints and then we are rearranging this term. Okay, so this is just rearrangement and we get equation number 1. So in equation number 1, we have this term lambda t comma xt. So if you integrate over 0 to capital T, then you have u into v integration. So after integration, you get equation number 2. Okay, so now this whole term comes here, lambda 0, lambda t, capital T, xt, and then this integration term will come over here. Okay, so this lambda dot t xt we put here, we put here, since this is not in the integration term. So now after rearranging all this, now we have one Lagrangian function which we have derived from the objective and constants which we have defined. The objective is to maximize the benefit. Constant is dynamic constants, that is function of change in stock over the time. Okay, now this function, that is flow benefit plus lambda times f, right? This function can be termed as h function. Okay, so this Hamiltonian function, so this is h function is known as Hamiltonian function, which will be function of rate of extraction, stock, time, and lambda t. Lambda t is the multiplier. Okay, so multiplier, because we have one constant which is continuous, therefore we have lambda t. Okay, now I put h value here and then other terms are same as equation number 3 here. Okay, after that, now this Lagrangian function, our objective is to maximize the benefit, right? So now to maximize the benefit, what we do is we differentiate the Lagrangian function with decision variable and equate it to 0, right? So now to differentiate it and then equate it to 0, our decision variable is rate of extraction y of t. So now let's say that y of t is changed to y of t plus delta t. Okay, if y of t is changed to y of t plus delta y of t, then x of t, the stock, will also impacted, let's say by delta x. So if your rate of change of extraction, if your rate of extraction is changed, then your stock will also impact it. Okay, so now I will try to find the delta L when my yt, rate of extraction, is a change from yt to yt plus delta y. What will be the change in my objective function? Okay, so now here this h dot will be function of y as well as x. So I get this whole two terms. Let's say dou h by dou yt delta yt, dou h by dou xt delta xt, whole term. Now this xt will be changed by delta x. So lambda t dot delta x. So whole integration dt. Now this term will also be dependent on the xt, right? Stock. So now f dash t, that is differentiated with respect to stock, and then delta xt. Then this term will also be dependent on xt. So lambda t delta xt. So whole term you will get as a function of delta L. Okay. Now we get this whole term and we have to equate this to the 0, delta L equal to 0. Okay, so you can look into it later on also. I'm moving on because I have little more slides this time. So now let's say that if you equate this delta L function to 0, now since delta yt is not equal to 0, this term have to be 0. So dou h by dou yt equal to 0. Okay, and then these two terms should be equal so that it equals to 0. So now lambda dot t equal to negative of dou h by dou x from this term, and then finally the third condition is f dash dot is equals to lambda t. Okay, so these three conditions are known as maximum principle, the condition of maximum principle, and this whole optimization process is known as optimum control. Okay, so this derivation if you look into it little bit, then you can understand it. The main important point here is that we derive three main conditions. Okay, so these three are very important. The change in Hamiltonian with respect to extraction rate is 0. The change in multiplier with respect to time is equal to negative change in Hamiltonian, and the change in the scrap value with respect to xt equal to multiplier, okay, lambda t at capital T, that is my time at last. Okay, so now what the lambda represents, what my multiplier represents, right? So this multiplier is converting the stock to benefit. So now this v is benefit, right? What is your flow benefit? However, f dot is function of stock. So what we have is lambda represents the change in stock or marginal benefit of keeping the resource intact instead of using the resource uh, right now. Okay, so or it is the marginal benefit of preserving resource. So this lambda is what is the benefit of keeping one stock, like one unit of resource right now, so that right now for tomorrow, so that your whole objective function is increased. So that is the, like, if you keep one unit of the change in objective function with one unit of stock, so that is given by lambda. Okay, so marginal benefit of preserving resource. So since lambda t is attached with the state variable, it is called co-state variable. And uh, now let's say that we have h, which is Hamiltonian value, which have present benefit, that is flow benefit, and future benefit, that is stock benefit. Okay, now after that we are trying to find the discounted value. So either you can discount the flow or you can discount the stock. So flow benefit, if you convert to the stock benefit, then you will multiply this e to the power minus rt term. So when we have discrete case, then what we do is we are multiplying the term 1 plus r, right? So in this case we have to do e to the power minus rt to discount the value of b dot to present. So this present value Hamiltonian, we will multiply v dot with e to the power minus rt, and in current value Hamiltonian, the stock value is, the stock benefit is converted to the flow benefit. Okay, so in this case, then what we will do is we will multiply the lambda f dot term with respect to e to the power rt. Okay, so these are the Hamiltonian value, and then from here we have again deriving. Uh, Now let's say that you have lambda t, which is the marginal benefit of preserving resources for future. If you discount it for future, then you get rho t. Okay, so lambda t is equal to rho t e to the power minus t, where rho t is where rho t or lambda t times e to the power rt is the current value of co-state variable. So if you find the let's say that lambda t is for the future, where time can be anything, right? So if you have to discount it, then you get rho t, and you are again multiplying this whole term with e to the power minus rt, so you get rho t times e to the power minus rt. So these are all derivations which you have to look by yourself also, so that you can understand better. So now we have lambda dot t equal to, now what we are doing is we are differentiating this lambda t with respect to time t. So now lambda dot t, So you have to differentiate this term, which both the term are function of time. So differentiation of u into v. So you have rho dot t e to the power minus rt minus, you will differentiate the second term. So you get r into rho t e to the power minus rt. Okay. So now we multiply both sides with the e to the power rt, and then we get finally the value of rho dot t, that is current value of co-state variable which is differentiated with the time t. Okay, so this whole equation which you have derived is known as second order necessary condition. Okay, now we have three principles, so which we have derived from here. We have said that the differentiation of Hamiltonian with respect to the yt is 0. So from here uh, what we have obtained is that we have current value Hamiltonian as this function, right? And so let's say this is my this function, and I'm differentiating it with respect to yt, and then I'm equating it to 0. Okay, so from here I get this, and my lambda dot t. So this is my this is again derived from the second or three principles. So I'll show it one more time. This lambda dot is equals to minus of dou h by dou x. Okay, so lambda dot e to the power rt, and e to the power rt is multiplied on both the side, that is the difference. So this is another thing. Now from here, let's say lambda dot e to the power rt in this SNC equation. Okay, so this is the equation. So now I am writing lambda dot e to the power rt as rho t minus r rho t. Okay, so from here I'm writing lambda dot e to the power rt value, and then this is equal to the change in the current Hamiltonian function with respect to stock. So from here I am again rearranging this term, and I'm getting rho dot t is equals to this value. Okay, so these are all derivations which we will use to understand the non-renewable resource utilization. Okay, so any questions in this slides, then you can ask me, then we will move forward. So
Madam, apart from derivation you have explained so far, what are the
mhm,
key points we have to remember
okay.
as part of dynamic optimization?
Sure. The one of the important part right now, the main point which we have covered is the representation of objective function and the constraints. Okay. After that, the process is that we have find the Lagrangian multiplier. Okay, and then we have defined the edge variable, which is known as Hamiltonian function. We have derived three conditions, which is also important. These three conditions, that change in Hamiltonian is equals to 0. So after these three conditions, now we are comparing it to the non-renewables thing, how it is like what is the implementation, that we will cover in the next slide, and then maybe I can answer it better. Okay, so now let's say that we have non-renewables. So till now we have only derived the things. So we have three principles, and then we have one SNC equations. Okay, second order necessary condition equation, that is it. So now from here what we are going towards is that we have a non-renewable resources where the rate of extraction is defined, that is yt, and price is defined, that is pt. Okay, now if you have to find the revenue, so the revenue will be price into rate of extraction, right? PT into YT, if you multiply, then you will get the price per unit and the rate of extraction. So from here, you are getting the revenue which you are generating, and you have cost function, cost of extraction, which will also be dependent on change in yt will be my rate of extraction, xt will be my coal stock of resource, anything. So the change in cost with respect to rate of extraction is positive. So if you extract more, the cost will be higher. However, if the stock is more, if XT is more, then the cost will be lesser, so less than 0. So this is positive impact and this is negative impact for the cost of extraction. Okay, now we are deriving the net revenue. Revenue will be your cost of extraction, your revenue minus the cost which you are incurring in extraction of resources. Okay, so this is PTYT will be my revenue which I am generating, and C function will be the cost which I am incurring. Okay, so now let's say that if you are non-renewable owner, then your objective is to maximize your benefit, right? So the maximization, so the dynamic optimization function which you are currently defining will be this function, maximization of your benefit over the time period T. Okay, so now your constant will be dynamic constants. In this case, the change in stock will be equal to negative of rate of extraction. So the more you extract, lesser will be the stock. So the stock will decrease with optimal with the rate of extraction, and your objective is to maximize the net revenue. Net revenue is revenue minus cost of extraction. So any question here?
No, no, madam.
Yes, sir. So I hope that you are relating with the. We will relate at the end, but till now, if you are with me, then it's more than enough. Uh, Now let's say that we have to find the, let's say that in dynamic optimization, we have current value Hamiltonian value, right? So the current value Hamiltonian function in this case is, so in dynamic optimization, we have to define the current value Hamiltonian function and differentiate this with respect to yt and set it equal to 0. So that is our step which we will follow in the next slide, this slide only. So now my current value Hamiltonian is defined as my benefit minus my opportunity cost. Okay, so this H dot is my current value Hamiltonian function which I am deriving from this objective only, and my first order condition and second order condition are previously which we have derived as change in Hamiltonian function with respect to yt is 0 and this one, right? So these are previously derived from conditions and we are using it right now only. So now if you differentiate h with respect to time and then set it equal to 0. So if you are differentiating this whole, so pt is equals to c dot t c prime t plus rho t. So this yt will be cut, right? This yt you will differentiate with respect to yt, so you will not get. So at the end, you get this price function. So the main important part here is that you get the price equal to marginal cost of extraction. So C prime, that is cost divided by yt, right? C prime of dot in this case will be equal to d cost by dyt. So this is my marginal cost of extraction, and this rho t is the shadow price of the resource. Okay, so this is very important conclusions which we are deriving, that the price is not only equal to the marginal cost of extraction, but it is also associated with the shadow price. Okay, so now in the second order condition, we have rho dot t is equals to r rho of t minus change in Hamiltonian function with respect to x. So this term will be equal to change in cost with respect to x. Why? Because in the Hamiltonian function, the only x dependent term is this c term only. Okay, so now from here what we get is that the rho dot t equal to r rho t plus r times change in cost with respect to change in stock. Okay, So now let's say that my change in cost with respect to change in stock is 0. So my cost of extraction is not changing with respect to time. Then this rho dot t times rho t equal to r. So this is first observation or first summary, and second summary is that when there is no stock effect on the cost of extraction, shadow price would grow at the rate of discount rate. This r is my discount rate, right? So even though there is no stock effect, so even though there is no stock effect on the non-renewable resources, then also the the shadow price of non-renewable resources have to grow at the rate of interest or at the rate of discount rate. So this is the second conclusions. So now here let's say that dou c by dou xt we have defined marginal benefit of not extracting resources, and R rho T is marginal cost of not extracting the resource. So this is your cost function that you are not using resource right now, but you are keeping it for future, and this is your benefit function. So now you are taking the equilibrium condition. So if you are keeping a resource in the future, your cost and benefit should be equal, right, at equilibrium. So then you get this R rho T equal to the change in cost with respect to change in stock. From here, if these two terms are equal, so in, like, let's say equation number star, if the right hand side both the terms are equal and they are in subtraction, so now we can say that rho dot t is equals to 0. So now we can say that the resource owner is indifferent when there is no capital gain. So now the capital gain, let's say that you have a resource and you are keeping it for future, however you don't have any benefit out of it, that there is no capital gain, then you are fine whether using right now or you are fine whether using in the future. So that is the inferences from the equilibrium condition which we have drawn. So now at equilibrium, so this is the same equation number star we are writing again. So at equilibrium, today's benefit of extracting the resource should be equal to tomorrow's benefit of not extracting the resource today, or your cost of keeping it for tomorrow will be equal to your benefit of future. So then only you will get the equilibrium condition. Okay, so then r rho t is the today's benefit, total benefit of extracting resource today, and the future benefit have two terms, that is stock effect on the cost of extraction and capital gain. Capital gain is represented by rho dot t, and stock effect is dou c by dou xt. So we can say that uh, so this is the that if you keep the resources for future, then there are two components, capital gain component and stock effect component. And even though there is no stock effect, let's say that if this change in dou c by dou xt is equals to 0, then also the shadow price have to increase at the rate of interest. So these are the few conclusions which we have drawn from this dynamic optimization. So I'll summarize and then you can ask me the questions. Okay. So in this optimization problem, we have a stock of resources xt, and we have yt, which is the extraction rate, and pt is the price of extraction. So now we have defined the revenue function, which will be equal to price time the yt. Okay, and cost of extraction, which will be function of yt and xt, and the assumption is that cost of extraction is positively related with the rate of extraction. So more is the extraction, more will be the cost of extraction, and when there is more stock, the cost of extraction of resource is less. And our objective is to maximize the total benefit from time 0 to time capital T, and our benefit is flow benefit and scrap benefit. So what we have done is we have optimized with we have optimized first setting up a Hamiltonian function and then differentiating the value of current Hamiltonian function with respect to decision variable, which is my yt, and then we send it to equal to 0, and from here we have uh, we have uh, we have get the cost price. So price is equals to marginal cost of extraction plus shadow price. So shadow price is represented by rho of t, and this shadow price as similar to augmented marginal cost equal to marginal user cost plus marginal extraction cost. We can say that shadow price is equivalent to marginal user cost, and it is associated with the opportunity cost of using the resource today. Okay, so when there is no stock effect on the cost of extraction, shadow price, let's say that this term, when this term is equal to 0, then shadow price would grow at the rate of discount or interest, and over the over the time price would grow with the rate of interest at least. Otherwise, there is no incentive to preserve the resource for future. So these are the conclusions, and the main derivations which we have done is the price derivation, which is equal to marginal cost plus shadow price. The shadow price indirectly shows the opportunity cost of using the resources right now, or the cost of utilization of resources right now. And then we have also said that the benefit of keeping the resource in the future have two terms. First is stock effect of cost of extraction, and second one is the capital gain. So now maybe we can discuss it with some questions. Sir, are you able to understand?
Okay, madam, partially, but
Okay.
see, my question is okay. I'm trying to go beyond what you derived.
Mm-hmm.
See, this dynamic optimization is relevant only for non-renewable. Am I correct?
Yes. Yes, we can say so. Yes.
Okay, because as we use it, the resource gets depleted, and the
Mm-hmm.
cost of extraction or user cost will keep on increasing. Am I correct?
Yes.
Yeah.
Yes.
Okay. Um, what about renewable? For example, if there is a case where the renewable resource also is growing every year.
Mm-hmm.
Okay, this is a hypothetical case, but actually this is real. The renewable resource like
Mm-hmm.
forests are growing every year.
Mm-hmm. So what are you trying to compare the renewable and non-renewable source, right?
Ah, yes, yes. Yeah,
So
in renewable where it is not depleting, it is growing every year fast.
uh-huh.
Okay.
Okay.
So in that case,
Okay, I got your
I,
point.
mm,
In the next section, maybe we can ask. We can in the
yeah,
renewable case also we are comparing. Let's say that in the now we were talking about non-renewable, right? So now in the
right,
future slide, let's say in the renewable case, the equation is
right,
same. Maximization
okay,
of benefit, right? Let's say that you have
right,
some renewable resource, then your objective function will be same. That is maximization of your benefit, and your constants in your constant here in the non-renewable case what we do is x of t is equals to minus of pi of t, that we have done, right? So now there is specific function g of t. Okay, so sorry, so this g of t represents the growth function is there. Okay, so let's say that you now in the slides which sir had taken lecture, he had taken the example of a pond. Okay, so you have a pond, and the pond have its own the fishes in the pond have its own growth rate, right? And yt is your catch rate, that how much you are catching the fish. Okay. And your constraint is that what is the change in the stock of fish? Okay. The change in the stock of fish will be function of growth rate of fish and the extraction rate of the fisherman. So are you able to compare these two a little?
Yeah,
So
yeah,
the
yes.
the only
And
difference is that here we have the growth rate into the constants. Okay. And yeah, in the renewable case also we are doing dynamic optimization, and we have drawn a few conditions in the renewable case also. So I'll move forward a little faster so that maybe we can compare it. And in the non-renewable cases, as far as we can conclude, are few important points is that the price will involve shadow price, which is function of rho, and it is similar to marginal user cost, and the benefit have the stock effect and capital gain effect. So capital gain effect should be always there, and it should be at least grow at the rate of interest. So let's say that you have any coal stock, and if the value of coal is not increasing by the rate of discount, then it is not of no use for keeping the stock for next year, right? So that is the summary. Now we are moving towards the renewable case. So if we revise, then non for non-renewable resources, we have derived a condition that total benefit rho total benefit R rho of t should be equal to capital gain plus the stock effect. Okay. So plus the total benefit that you will get tomorrow, that is the stock effect. Okay. So now we have all stock effect and capital gain which we have derived. Now in the renewable case, now we are taking first scenario, that is biological model. Okay. Now let us assume a lake which is full of fish and a remote place. The fish are identical in structure and uniformly distributed over the lake. And in the case 1, it is not disturbed by human being. There is no economy which is being involved, and it is purely biological setting environment. So now the growth of fish is also called the stock dependent growth, because the growth of fish will be dependent on the stock of fish. Okay, where xt is the stock of fish, that how much fish is there in the pond. Now I have drawn we have drawn a graph where my x-axis represents the stock of fish and y-axis represents the growth of fish. Okay. Now the growth of fish will be function of stock of fish, and the curve represents this. So now let's say that O to A, this OA, and then there is a growth and then downwards, right? So this curve, let's say that x minimum, OA is the x minimum. Okay, so if the stock of fish is less than x minimum, let's say that in this case till O to A, if the stock of fish is less, in this case the fish will extinct or the fish will exhaust. Okay, because we don't have minimum value of stock which is needed in the pond. Okay, after that, with increase in stock of fish, the growth of fish will increase till point P. At this, maximum growth is represented, and this maximum growth is shown at the point where the stock is xmsy. This is called maximum sustainable yield, MSY. Okay, so here we get the maximum sustainable yield. After maximum sustainable yield, with increase in the stock of fish, the growth of fish reduces. So this whole curve is for the case when there is no human intervention at all. Even then, the growth will decrease. Why? Because so now in this case we have two roots, that is xc and x minimum. So the function have two roots, xc and x minimum. X minimum is the minimum stock required for the species to grow. When the stock of fish is less than x minimum, the fish will get extinct, and beyond x till x msy, the growth of fish will increase and we will reach to maximum sustainable yield. After xmsy, we reach towards xc where growth becomes 0. So why after point P, the growth becomes reduces. So this is because of the competition for the food and oxygen. So we derive this curve for the pure uh, independent case. So in this, if you have any question, you can ask me. So if you have any
Yes.
question with a variable also, maybe.
No questions. No questions.
Okay, so I
Understood.
move forward. Now, like let's say now we have optimum extension of renewable sources in the economist model. So, पहले we have biologist model. Now we have economist model. Human discovered commercial importance of fishes. Economics enter into this case. Now, let yt will be the rate of catching of fish. Xt is the stock of fish, and cost of catching the fish is represented by c function. Now my objective is to maximize the benefit. So benefit will be price, sorry, the benefit will be revenue minus cost. Okay, so and then e to the power minus rt is multiplied to find the present value of the whole benefit. So and then my constants is similar to the non-renewable cases where change in stock of fish. In the non-renewable cases, we have only this term, but we have added this growth term also. Growth will be function of stock of fish. Okay. So now we have derived the Hamiltonian function. So as in the dynamic optimization, we do derive the Hamiltonian function. So benefit minus the rho times g dot minus yt. So this term. So this Hamiltonian function is purely mathematical. And then we have first order condition. So in the first order condition, differentiation of Hamiltonian with respect to decision variable is 0. So now if you differentiated this equation number star with respect to yt, then you get that pt is equals to c prime t plus rho t, where C prime T is marginal cost of extraction and rho T is the shadow price. Okay, so now price would be equal to marginal cost of extraction plus shadow price. Okay, now we are differentiating Hamiltonian function with respect to xt. Previously, we have differentiated with respect to yt. Now we are differentiating with respect to xt, and now we have get change in the cost with respect to xt plus rho times change in g with respect to xt. Okay. So now, if you multiply negative term on both the side, you get equation number 1. And we know that the condition which we have derived earlier, that rho dot t is equals to this. Now we have this equation. So instead of this, what I'll write is rho dot t minus r rho t. So this equation star is put into equation number 1, and you will get equation number 2. Okay. So now from 1 and 2, we are equating rho dot t is hold this, then we have get equation number 3. So if you change make some changes in the equation number star, you rearrange the term, then you get equation number 2. Then if you insert equation number 1, equation number 2 into 1, then you will get the equation number double star, and then you get the equation number 3. Okay, so in equation number 3, you have in the left hand side you have r times rho t in the right hand side, and in the left hand side you have three components: rho dot t, change in cost with respect to stock, and rho dot t times change in growth with respect to time. So now we have this whole equation number 3 gives us the total benefit of preserving the renewable resource for tomorrow. So the first component is capital gain component of keeping the resource for future. The second component is stock effect on the cost of extraction. That what will be the effect of the stock on your cost of extraction. And the third component is benefit due to biological growth. So because you have certain stock, your growth of fish will be higher. So that will be the third benefit. So these are the three benefits which we have derived in the renewable cases. In the non-renewable cases, you don't have this term, third term. Otherwise, it is similar. So total benefit for preserving resources have three components: capital gain, stock effect on cost of extraction, and benefit due to biological growth. So it is not there in the context of renewable cases. And ROT is total cost of preserving the resource for tomorrow. Okay, so this is my ROT. That is my right hand side component is the cost, and left hand side component is the benefit. So from here we can say that when the cost of keeping the resource for tomorrow and the benefit of preserving the resource are equal, then we achieve the equilibrium condition. And when this equilibrium condition is achieved, then we can say that the optimal path of extraction is achieved. So therefore, for optimal path of extraction, we have this kind of price condition and benefits which we can draw in the present or in the future cases. So are you able to understand? If you have any questions which I can clarify?
No, no, madam. I'm able to make sense. Yeah.
So did I clarify the changes in the previous case to the second case?
Yes, yes. Broadly, I understood. Only that growth part, that part is missing in non renewable. In renewable, that growth, the G of X of T, that is
Yes,
added. Yeah.
yes. Yeah, so let's say that you have a fish, okay. So the growth part is that let's say that you have certain stock of fish which you have left for tomorrow. Because of this fish, the growth will be higher and you will be benefiting more. So that is added in the renewable cases. Yeah, yes, yes. And other than this, the conclusions are there. Now, now we are moving forward towards the next part. So if there is no radical change in the demand, and cost condition. So there is no change in the demand or cost condition. Then first order necessary condition and second order necessary condition leads to a situation where the growth of stock x dot t is equals to 0. So there is no change in the demand or no change in the cost. Then the change in the stock with respect to time is 0. So no capital gain because capital gain arises due to change in stock only. So my x of t equal to 0 and my rho dot t equal to 0. So that is what we are saying is that let's say if I equate this term to 0, okay, and uh, and there is no change in the demand condition. So when there is no change in the stock, then my rho dot t, that is the change of rho dot t is the change for like rho in a way gives us that the shadow price or the change in the shadow price with respect to time will be equal to 0. So let's say that this whole term which we have derived, and at steady state this rho dot t equal to 0 since x dot t is equals to 0. And from here let's say that my when I equate rho dot t equals to 0, then I get this term from this. And I have also g of x is equals to y of t. Why? Because my x dot t is equals to 0, right? So my constant was that x dot t is equals to g of x minus y of x. So this is 0 at steady state. So these two terms are equal. And since rho dot t is equals to 0, this term are equal. So during the steady state condition, I'm assuming two things. X dot t is equals to 0 and rho dot t, change in the shadow price is 0. Then what I will get, okay. So now what I am doing is I am drawing the R curve. R is the revenue curve and the cost curve. Okay, cost curve for different X. The cost will be function of Y as well as X, but I'm keeping Y constant and change the X from X1 to X2. So if I change the stock, the cost will come down, right? So if I the curve 1 and curve 2, my x1 is less than x2. Okay, so C1, C2 are different harvest cost function curve and C is dependent on stock. X2 is more than x1, so C1 is more than C2. Because more is the stock, less will be the cost. Then R curve represents the revenue. So um, now, along the optimal harvest path, price is equal to marginal cost plus shadow price, as we have derived earlier. Now, based on the first order necessary condition, we have derived the optimal path, that is, price is equal to rho plus del C by del YT. Okay, so harvest price should be equal to cost of extraction plus shadow price. Okay, so shadow price is rho T and harvest price is del C by del YT. Now, okay, now again I'm explaining the graph only. So YT is the rate of catching fish and C of YT is the cost, and I have defined various harvest curve C1, C2 and so on based on changing the X value. Okay, X is my stock value and from here I get the R curve. Okay, so now I have based on my uh, optimum condition of price, that star, that price is equals to rho plus del C into del Y, right? So let's say that at M and N this price value I'm getting. Okay, so this M and N are the points where the optimum harvest condition is fulfilled, that is equation number star is fulfilled where price value is given, right? Now at M I get y1 and at N I get y2. These are optimum harvest value. Okay, when the stock value is x1, optimum harvest value when the stock value is x2. Okay, now I am trying to join this value. Okay, M and N and so on. Let's say here so on. So if we join points like M and where the optimality condition is satisfied, then we have a locus. So we have different curves. There is another curve, and then there is, let's say, there is another curve, and so on. Then if I join this whole points where the condition of condition which we have derived, that price is equals to shadow price plus marginal cost of extraction, is fulfilled, this M, N, O, P and so on. So this whole line is known as catch locus. Okay, economically optimal points of extraction, since these are following the optimal extraction condition which we have derived. So, any clarification which you want, or shall I move forward?
No, 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 madam.
Sir. So, are you able to understand this curve, sir?
Mm, okay, I only get. I see. I am still. I'm not tracking the mathematical
Uh-huh.
formulations, but I'm
Mhm.
trying to interpret my thing. So what you are summarizing, saying that is that the catch locus is the ultimate thing. If you anyone wants to optimally business to do fish catching, his point should be on the catch curve. Correct?
Yes, 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 that's correct. Mhm.
Okay, okay. Thank
So that is economically optimal, like curve for different stocks of this, right? So what we have done right now is we have drawn a harvest cost function, which will be dependent on uh, a different level of stocks to create the cost function. And we assume that along harvest cost function, there are points like M and N where first order necessary condition is satisfied or which are optimal extraction points. Then if you connect all this optimal extraction point, then you get catch locus, and y1, y2 and so on gives the optimal harvest. Okay. Mm, okay, that is it. Now what we are doing here is we are trying to overlap the catch locus and growth curve. So if we assume that cost of harvest is low or fish are highly valued, then revenue curve will be steeper and too much revenue will be generated. Also, since the cost of harvest is low, cost curve will shift downwards and catch locus will shift upwards because we want to have more harvest. So what happens is when when the cost of harvest is lower, we are moving from 1 to 2, 2 to 3, 3 to 4. So these are different, let's say curve 1, curve 2, curve 3 and so on. So these are different catch locuses or catch loci, and this graph is my growth graph, right? So this is my growth graph. So I am trying to overlap whole points. Now from here, uh, economically, I have many points at which the optimal extraction or optimal extraction is being done, right? So let's say that any intersection between catch locus and growth locus define a steady state, but all steady states are not stable. So this intersection point where growth locus are intersecting, let's say that here, here, let's say here and so on. So these are x1, x1, x2, x3 and so on. So these are all points where we can say that the optimum in the context of economy. So the optimum conditions for the economist is obtained where the steady state condition as we have defined are similar as before, where x dot t is equal to 0 and rho dot t is equal to 0. Okay, so now my x1, x2, x3, so on, all are optimum in the context of economy. Okay, now economy's optimum is defined by the steady state where growth is equal to rate of harvest, where gxt is equals to yt and x dot t is equals to 0. So we have all points from x1, x2, x3 and so on. And however, we have seen that biological optimum is only at the point x MSY. So economist's optimum may not always be same as biologist's optimum because biologists have only a single optimum while economists have many optimum points. So from here we are trying to derive the condition where biologist and economist optimum intersect each other. So now we have this function which we have derived, that is rho dot t is equals to rt plus change in cost plus this growth function. Now let's say that we are taking r is equals to 0 and change in cost with respect to stock is 0. Then we get r is 0, this term is 0. So okay, so we no, so for steady state we are equating this whole term with respect to equal to 0. So now if I have to make the rho dot t is equals to 0, then my rate of this should be 0 since this shadow price is not 0. This whole term should be 0 and this growth term should be 0 since rho dot t is not equal to 0. So we get three conditions. So if r is equals to 0, uh, if r is equals to 0, del c by del xt is 0, then and only then we get the biological optimum and economic optimum which is being converges. So from here we have different sets of economists optimum. However, in the condition which we have derived before, where r rho t plus change in this whole term, if we equate it to 0 and we take the conditions that rho t is not 0, now r should be 0, this change in the cost with respect to xt should be 0 and change in the growth with respect to xt should be 0. So at this condition, if we get three conditions true, then this condition will be optimum extraction pathway in the both economist as well as biological perspective. So we have get two conditions here. So yes, any points, sir?
No, 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 madam.
Okay, sure. Now, if at any point of time stock is more than x msy, so if at any point of time my stock is more than, let's say, this by the point where both the biological and economic optimal is intersecting, then uh, then it is of no use because anyway my growth is negative, right? My growth with respect to stock is negative. So if x is more than x msy, since del c by del xt is equals to 0, no benefit of more stock. That is the first condition. So you can extract the fishes more so that we reduce the x to, so x reduced to x msy. And when r is equals to 0, when rate of discount is 0, then there is no discount, so it is better to consume, sorry, to consume today than reserving it for tomorrow. So these are the two conditions where we get that biological optimum is achieved. So now, so this is the expansion of previous two conditions only, that r should be 0 and the change in the cost with respect to xt is 0. So now the price at which the catch locus pass through the point less than x mean beyond which species get exhausted. So this price is known as um an vanishing price or resource exhausting price. So this point A, where the catch locus passes through the point less than x minimum and the resource will get extinct at this point. So this point is known as the vanishing price or resource exhausting price, and the resource get exhausted under both private ownership as well as public ownership as well as open access. So the main reason for not knowing the main reason for extinction of resources is not knowing the x minimum condition. Okay, so this is not x min, this is the x min. So okay, any questions, sir?
No, 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 no.
Okay,
I'm trying to interpret myself the story. So
sure,
what
sure.
you are saying is, so if our rate of extraction is below the biological limit,
Okay, ha.
okay, then there is no then there is no benefit, or no benefit of future stock. Okay, uh, okay. I see. I'm trying to give a physical interpretation.
Yeah, sure, sure, sure.
For
Uh,
example,
uh-huh.
if the fish grows beyond x msy, then
Uh-huh.
anyway they are going to die. So
Yeah, yeah.
even so, even if you extract it, so not going to add much to the cost of future stock or something like that. Correct?
Yeah,
Yeah.
yeah. Let's say that
Yeah.
you have very much population of fishes in your tank, okay, and you said that no, I don't want to catch fish now, I'll keep it for tomorrow. So anyway the fish will decrease, right? Because the growth will be negative after a certain stock, right? So that's why it's better to use right now than to keep it for tomorrow. So did I answer?
Okay, okay, madam. Yeah.
Yes. So then we said that the vanishing price is the price matlab, below which the uh, fish or the species get extinct. So why? Because the stock of fish is very less. So here the locus curve is intersecting the x-axis. So at that point we get the vanishing price, and okay, and now what we are trying to do is we have talked about three kind of ownership: private, public, and open access. Okay, so now open access resources is where entry is open for anyone. Like let's say that there is a deep water, deep sea or ocean, anything. So anyone can go there and fish, right? So this kind of resources is known as open access resources, where there is no restriction for harvester to go and catch or go and use the resource. So now in this case, the rate of harvest of open access will be much more than rate of harvest of private ownership. Why? Because there is no any incentive for keeping the resource for the future. Why? Because anyone else will come and use the resources if I don't use the resource. So in this case, the rate of harvest in the present will be very high. So now uh, now we are comparing two scenarios. Okay, so in the case of private ownership, we have derived that price is equals to marginal cost of extraction plus rho shadow price, right? So marginal cost of harvest and yt is the optimum condition under private ownership. So now in the case of open access, there is no shadow price. Rho t will be equal to 0. So there is no any marginal benefit of keeping the resource for the future. So price will be given by cost upon yt, that is the average cost. So the price will be given by average cost rather than price equal to marginal cost plus rho t in the case of private ownership. So there is no benefit of not harvesting resource today as anyone else will do. So now we have drawn here the curve. So point A is the case where uh, this optimality is obtained and I get the y star t. Okay, and point B is the case for the private ownership. Private ownership, sorry, for the open access. My bad. Open access, and A is for the private ownership. Okay, so now in the open access case, I get YF. YF is optimum rate of extraction in the context of open access resources. And at point B, YF, that is rate of harvesting optimality, is achieved in the case of open access resources. So the rate of extraction is much more than the case of private, where we get Y star T. Okay, so the why it is because the harvester has to harvest more to get the break even point. Since uh, there is too many entries in the system, it is more competitive in the case of open access, and the cost of extraction will become higher. So to get through the break even point and to make benefit or to make profit, they try to extract more. So therefore we are intersecting the revenue curve and the uh, uh, we are intersecting the revenue curve and the cost curve here, and we get the point P. Okay, so now catch locus will shift upward and make the optimality point at the level where cost is equal to revenue. So that is called as break-even point for the harvester. So the harvester has to harvest more to make more benefit, because there is more entry into the market and more competition is there. Therefore, extraction is extraction rate is more. So, uh, any discussion or any comment on this?
No, madam. See, this is a situation. Open access
Hmm.
means can lead to tragedy of commons, right?
Yes, yes, that is what.
So
Hmm.
what you're saying is, in case of sea, for example, in a common sea and lots of fishermen,
Hmm.
doesn't it? Okay. Doesn't it lead to tragedy of commons, or is it assuming that because the resources are infinite? Uh,
No, we are not assuming that the resources are infinite. Since the extraction of resources is very high in the case of open access resources, it will lead to the tragedy of resources. Yes. So we will discuss in the few more slide, and then we will end. So I'll take another 10 minutes if it is possible. So we have another 3 to 4 slides. So now, in the case of open access resources, cost of harvest increase because of competition, and to meet with the cost, they will try to extract more. So now we have derived the.
Madam,
Yes.
why it increases? Cost of harvest increases. Cost of harvest depends on
The cost of
no.
harvest will increase because there will be many entry points. It will be dependent on the stock also. That might be one of the reason. But what we are saying is that there are a lot of competition, because it is open access to anyone, right? So anyone can enter into this market. There, the entry in the let's say sea or anything is easily available for anyone. So for that, the cost of extraction is higher. If you extract more, then you can make more benefit. So that is what it is trying to say, I guess.
Okay. Okay.
Did I answer, or you want to add some points?
No, no. I'm trying to visualize
Mm-hmm.
the cost of extraction means I'm trying to interpret physically. Is it the cost of taking the cost of how much time he has spent on the boat? For example, assume hypothetically the fisherman is paying a rent for a mechanized boat and taking it to the sea. He has
Mm-hmm.
to spend more time
Yeah.
to, but we are assuming the resources are the stock is growing more than biological. Uh,
The growth rate
okay.
is there, but let's say that for open access resources, they will not think about the future, right? So for now, I have to maximize the benefit. But since anyone else can also buy the boat and they can also come, to make, like, to, let's say that you have rent the boat, and then let's say per fish, you, the cost of boat will also include it, right? Because the cost of catching the fish overall, you will try to find. So if there is multiple entries into this, like into the extraction of this resource, there will be more competition, since it is like, since there is no property, uh, like property, what we say, patent to someone. So
Yeah, yeah. Everyone enters,
hmm,
but the sea is has a capacity to accommodate any number plus one.
okay. So
No.
in general, let's say that, yeah, I got your point, that let's say that it doesn't matter if a person increase by one. That is what you're saying.
Yeah, it is like Pushpaka Vimana, right? See, for
Hmm.
example, let's say there are, see, if it is like a river, I understand it is a limited one that the more number of fishermen join, then the fish gets depleted below the point of
Hmm.
whatever is the minimum, and then the whole becomes unviable. But in
Hmm.
case of sea, it is open access, and we don't bother about stock depletion because the rate of stock growth is much more than
Hmm.
uh,
Okay.
than harvesting.
Yeah,
Then
yeah. I got your point.
individual,
Mm-hmm.
yeah,
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 yeah.
yeah.
Please
So
continue.
yeah, basically see, I know, to just put it in a common English.
Mm-hmm.
See, so let us say the whole ocean is there. If
Uh-huh.
today, if the 1,000 fishermen is there and they're making money,
Mm-hmm.
they're making some money profit, let us say 100 rupees. Even if tomorrow, if you add another 1,000, 2,000,
Mm-hmm.
okay, they're
Mm-hmm.
still able to catch that much of fish. Of course, the selling price may be different because of too many fishermen trying to sell in the market. The price of
Mm-hmm.
fish may come down, but
Mm-hmm.
their ability to catch a harvest is the
Mm-hmm.
same for all the fishermen, right? That never gets diminished. Hmm. Hmm.
Mm,
There you go.
I got your point.
Uh, I see. Basically, I say I'm not an economist. I never studied economics course. This is the first time I'm
Mhm,
doing this.
mhm.
I'm an electrical engineer. So as
Yes.
just a hobby, I'm trying to visualize.
Okay.
Okay. So it is. There is nothing like point of diminishing returns. Okay. In case of open access, where see, tragedy of commons is, I think it is applicable to uh, a limited area where the rate of extraction is more than the rate of growth.
Mm-hmm.
Okay,
Mm-hmm.
then the resource, for example, yeah, for example, in agriculture, you take
Yes.
okay, you are supposed to use soil at a particular crops and a particular time, and if you are greedy and you're cultivating too much or something, then the
Mm.
soil gets eroded. Afterwards, it becomes a desert.
Yeah.
Okay,
Mm-hmm.
diminishes. Okay, but
Mm-hmm.
such a thing won't occur in the sea. That's what I'm assuming. Is it?
Acha.
Maybe my assumption is.
Uh,
Huh?
matlab, if I got your point in the case of sea, but let's take another, like, let's say, let's take a forest. Okay. So, a forest, if it is a tribal thing, that there are a lot of tribal people staying there and they are deriving certain extracts of benefits from the forest. Let's say that honey, let's take the example of honey. Then, since there is no, what we are trying to, matlab, take the explanation is that since there is multiple entry system and there is no restriction, the benefit, or what we say, the per unit price will reduce. But to make like, to make a profit out of it, I'll try to extract more honey and then sell it, uh, as other people are also selling it. So that is what I have derived from this explanation, that the cost will increase because anyone will come into this business and they will try to uh, do that, right? So to make my business viable, what I will do is I will get more, and therefore the extraction is more in the case of open access. So that is what I have observed. But since when you're asking about the sea, where the growth rate is very high, and then we are taking the example of C in the case of open ownership case, then there is a problem, but I have to look into it more.
Okay.
So yeah.
For example, in case of solar energy, let us say solar energy today we say it is abundant.
Mm-hmm.
Okay.
Mm-hmm.
So there is nothing like there is stock. Stock is something like
In the
infinite,
case of
and
solar energy, though, I don't think we can apply this logic. Why? Because this solar energy is in abundance unless there is land issue or whatever it is, other thing, right? Uh, Sir, please give me
yeah,
1 minute. I'm getting very
yeah,
urgent
yeah,
call.
okay, okay.
Give me a minute.
Yeah, sure, sure. Yeah, maybe you can summarize and
Sure.
close.
Hello. Hello. Mama, klase nad Mama, zapiszę. Hello, sir, am I audible?
Yes, yes.
Okay. So, yes, in the case of C, I cannot relate it right now because since you say that the growth rate is very high and it can cater more number of people as it is large enough. In this case, I have to look into it. So, if you
Okay.
have any idea, then maybe you can add it.
Okay. Yeah, okay, sure. Okay. Okay, maybe you can summarize it, madam. I think we are run out of
Sure.
time. Yeah.
So the divergence between the marginal cost and average cost pricing. So marginal cost is in the case of private ownership, and average cost pricing is in the case of open access ownership. Then this divergence or this difference is known as congestion externality. So since the cost of harvest is increasing because too much congestion or too much people enter into this, so as too many harvester comes into it, so this congestion externality can be derived from this difference curve. So del C by uh, del YT minus C upon YT. This is the cost which we have derived in the case of uh, this we have derived here, average cost. This two difference, that is marginal cost minus the average cost, is termed as congestion externality. So because of the congestion, because of the interference entry of many harvesters, since it is an open access resource, there is the congestion, and it is called as congestion externality. And to solve this condition externality, then we have taxation system. So two-part tax system should be there, where tax should be equal to rho t times del this congestion externality part. Okay, so this rho t we have derived as a shadow price, and this term which we have derived as a congestion externality. So this difference, if you add into this cost component, so price is equals to whole this, then you get cut. So finally you get uh, your externality gets reduced, and the price will be dou c by dou yt plus rho t, as similar to private ownership, right? So in the we have faced the problem that in the open access case, we have average price is equals to average cost. However, um, uh, due to congestion externality. However, in the case of a private ownership, price is equals to marginal cost plus rho of t. So to eliminate the externality, what happens here is that we are imposing the tax, where tax amount is equal to this, and this rho plus this whole term, if you enter into the cost component part, then you get the price which is similar to the private ownership part, and our externality get eliminated. However, it is two-part taxation system is attractive theoretically, but if you have to implement practically, then it is not so easy. So another system is that quota system, that you can give certain part of C to one country, another part of C to another country. So it is quantity wise rationing. And as we have discussed the taxation system, it is called price rationing. And so these are the two things, that is price based rationing and quantity based rationing, to solve the externality problem, due to which externality in the open access case, the open access resources are there because we are not able to give any kind of property right to any specific entity. So then we have uh, tragedy of commons. And then we have discussed the solution to tragedy of common. So tragedy of common can be solved by community-based management or collective action, where we can give the property right to the whole group as a common property resource, right? And then the whole governance system is at the local level, and then all the people will come together, and then they will decide accordingly. Also, there will be a community leader who will ensure that all the people are participating. So uh, all the people are participating in the case of management of resources, in terms of money as well as time, and no one is free riding. So since benefit is getting to the whole community, there are many people who might be benefit like taking benefits unnecessarily by as a free rider. So this can be reduced by a leader. So if this community based management failed, then we can move towards the privatization. So the privatization have a negative impact also. So these are the solution to the tragedy of commons. And the negative impact of privatization is that even though the privatization improves the efficiency, it will lead to the decrement in the equity or equitable distribution of resources. So many of the people or many of the individuals are solely dependent on common property resources. Let's say that the tribal people are fully dependent on the resources from forest. So if you privatize these places, then it will adversely affect their livelihood. So that is the negative impact of privatization. So if we conclude, then we can say that poverty and environmental degradation have two-way relationship. So let's say that if someone is poor, then they are more reliant on the resources. They will try to extract more resources. However, since they are trying to extract more resources, there will be fewer resources which will be available in the nature, which will lead to the person even more poor. So since the dependency of that group of people or that people is totally in the local resources, so there is a loop system that I am poor, I am depending on the resource, but when I extract resource, the resource get depleted, and now I don't have any more resources, so I'm more poor, or I don't have any resource now. So this is a closed kind of environment. And in this case, if this kind of resource are given to some private entity, or if there is some developmental projects in these places, then it will totally impact the livelihood of locals and poor people. So in this kind of relation where due to environmental degradation, the poverty gets worse when the resource is negatively impacted, there needs to be careful thinking about the impact due to developmental projects. So, since the environmental degradation or degradation in resources have negative impact on the well-being of people, before putting any kind of developmental project, there should be proper planning and judicial study about the impacts. And to project this type of resource from being a tragedy of commons, we need to carefully think about the institutional arrangement, whether it can be managed by community, or it can be privatized, or maybe it can be same as the open access resources. So that should be properly managed. So with this, I will conclude today's session. I will end today's session. So any questions from the last three slides, or we can end the session?
No, madam. No, madam. I had to study myself. So I
Sure, sir.
think we have one more session. Huh? Is it before?
Now, this is still the week 12 session as I have covered, but one like another guy will also cover the same lecture in the next Tuesday lecture. So, the week 12 is left on Tuesday. After that, there will be a extra class, which is scheduled somewhere in the before the exam. So, yeah, two more
Okay.
sessions.
Okay, madam. So one thing which I find is there's too many variables to keep track in our mind.
Uh,
That's and
yes.
yeah, because I am telling you because I'm not an economist. Okay, I
Uh,
understand mathematics, but see, the difference between economics and mathematics is 100% abstract, but
uh-huh.
economics we have to correlate with reality with examples and
Yeah.
real life. So that
Yeah.
is where then only we enjoy, right? For example, all
That's
that
correct.
demand curve, supply curve. Okay,
Mm-hmm.
okay. If you keep on talking in that language, then we are disconnecting with reality. So my
Yes.
feeling is that now and then we have to pause and say what for we doing this. So where
Mm-hmm.
it connects in real life. So some things I understand, like tragedy of commons, what happens,
Mm-hmm.
open access, what happens,
Mm-hmm.
if there is no taxation on environmental goods, what happens, if
Mm-hmm.
pollution abatement cost is not there, what happens.
Mm-hmm.
So what is the optimum level? Okay, some things we understand. Okay, but
Mm-hmm.
so sometimes what happens is when we get into too much mathematical, we lose track of the connections.
Yes. Yeah, that
Okay,
is correct.
so
Like,
that.
especially in the case of dynamic optimization, we have a lot of derivations also. So
Yeah,
after
maybe
derivations,
what I suggest is maybe I see I have noted down in my notes, but I am not going to focus on it. That's why I just asking. Okay, okay. When you put everything dynamic optimization as a black box, okay. Ultimately, what is it's trying to find out the optimum parameter. That's it. Okay.
yeah.
So based on changing with the parameters, stock is changing with time and cost
Mm-hmm.
of extraction is changing with time. So what is the optimum rate of extraction? Whatever it is. So what
Mm-hmm.
is the outcome? So so what I believe is now and then we have to pause, make it everything as a black box. Okay, that is
Mm-hmm.
leave it to optimization experts, Hamiltonian or something. What is input? What is output? Okay,
Yeah.
so yeah, the output is one, and then connect the input and output that model to the real world.
Mm-hmm.
So that's what I'm trying to do. Actually, while you're explaining, really speaking, that there's all this mathematics going above my head. So I'm trying
Mm-hmm.
to connect. See, I can follow up to the normal optimization, like
Mm-hmm.
that normal optimization. But when it comes to dynamic optimization, I think it really crossed my head. So
Mm-hmm.
I
Yeah.
but otherwise, yeah, it's okay. It's okay. So only thing is. I think I think one summarization class would help to put all the concepts together and sequence. Okay, because
Sure.
every model or a concept is a improvement over the previous. Okay,
Yeah, that is
so
correct.
so when I start reviewing the lessons from week one onwards,
Mm-hmm.
so every theory is a Kose theorem or Portas. Everything is basically improvement over the other.
Mm-hmm.
Okay, something is missed in the previous one. This fellow has done improvement, and then this causes this one, this causes this one. Maybe that chain, no? That chain
Uh,
of theories
mm-hmm.
is when during the summarization class, okay,
Mm-hmm.
without getting into specific details of any of these things, the
Sure.
overall big picture, okay,
Okay.
that will help. Whatever is the next class, just to
Mm-hmm.
summarize the whole thing, yeah, that will help. Okay, so just,
Sure, sir.
yeah, that's it.
In the next Tuesday, another guy will take the class. After that, there will be a summarization class. So during that, I will try to get the like a real summary in the theoretical terms, that what we can like what is the overall picture of first to last things which we have learned. So yes, I'll try to do that
And
in the.
with specific example for each theory. Okay,
Mhm.
so maybe yeah, maybe that will help.
Sure, sir.
So yeah, oh, okay, madam.
Okay.
I think
Okay.
thank you very much, madam. Thank
Thank you. Thank you for joining, sir. So if you have any question also, then you can ask me in the mail or on the portal. So otherwise, so you have very good understanding. So I'm really glad that we have interacting, because many a times there are few things which we also miss, because I also try to
you.
cover up things and then
No,
I
no.
learned by myself.
See,
But
the reason is, see, I'm not a normal student. I'm not writing for marks or anything, just last
yeah.
minute what is important. I'm trying to, as a hobby, I'm trying to learn economics. So I did econometrics course last semester, and this semester I'm doing this environment because that is a very hot topic these days.
Mm-hmm.
So I'm not pressurized for marks. So I'm trying to
Sure, sure.
make sense of how economists think when environment comes into picture. Basically, I'm trying to think.
Mm-hmm.
Normal economists versus environmental economists. So, what are the additional things which bothers them, and how they address it? Okay.
Mm-hmm. Yes.
So in that context, I think I have got up to 70% I understood. That's